getting things going for today, we're going to be working with 10.3 and 10.4, primarily dealing with triangles, and then the more generalized idea of working with polygons. So working with some specifics and then expanding on that, and then we'll see that once we get into polygons, it's kind of a mess of different things that we can work with in there. So start small and we'll expand. So first things first, with 10.3, we have some vocabulary that we need to go through. And this vocabulary is not unique to just the 10.3 material. It's not unique just to triangles. This goes for a lot of different forms of geometry and basically polygons that we're going to be working with. So one of the big ones that we have is our word congruent. It's kind of a fancy way of just saying when two or more things are equal to one another. So if we were told that angle A is congruent to angle B, it's the same as saying angle A is equal to angle B. So it's a more commonly used phrasing that we have primarily for geometry. But again, at its core, it just means this thing or these things are equal to one another. We then have interior angles. Those are angles that are contained inside a given shape. Again, that could be a triangle, it could be a square, it could be an octagon, pentagon, whatever it may be. And exterior angles are angles that are created along the outside of a given shape. And we'll go through a couple examples of seeing these here in a quick second. I think it's with some of these other ones down here. But we'll go through an example of exterior angles here in a little bit. Now looking specifically at some triangle relationships now. So again, generalized, this goes for all of geometry, and now we're focusing in for triangles specifically now. The sum of the interior angles of a triangle is always 180 degrees. And this doesn't matter if it's a really nice right triangle, like we'll get to down here. Doesn't matter if it's a really nice right triangle, if it's an obtuse triangle. We'll go through these different classifications. Doesn't matter the actual raw shape of this thing. The interior angles will always, always, always add up to 180 degrees. We have another relationship that shows up here with triangles, an interior angle and its adjacent exterior angle are supplementary. If you remember back to our terminology that we were working with from yesterday, supplementary means that the two angles add up to equal 180 degrees. So we'll go through a couple examples here. I'll make up a few with this. And we'll go through seeing what the interior and exterior angles look like and actually solving for a couple of these. So we'll jump us over to the whiteboard. And we'll make up a triangle here really quick. So we have a triangle there. Now I'm going to do these in two different colors, just for the sake of seeing it. So we have angles A, B, and C. These are all interior angles because they are contained inside of the shape that we're working with. And now the idea of what is our exterior angles? Well, that could look something to the effect of, expanding on these here a little bit. I'll do this in red. It's not drawn perfectly to scale, but follow along with me on that. We have angle D, E, and F, and those are directly on the outside of our triangle that we are working with. And this is where we get these as exterior angles, because it's on the outside of our shape that we are working with. Now again, as we were just told in the notes, we were told an interior angle and its adjacent exterior angle are supplementary. So if we're looking specifically at the bottom right corner, angles B and E, means these two things are supplementary to one another. If I add angle B with angle E, those two things should add up to equal 180 degrees. So a couple ways we can see that written out, just showing you guys the notation of what you can see with this. I'll use the one that we just went through. So the little sign that's out front here is supposed to look like an angle. I can't draw it as effectively as the book might show it, but we're supposed to have something that's going to look like an angle showing up in there. So again, an interior angle and its adjacent exterior angle are supplementary. So I'm just listing out the three that we have here. The three pairs that we have displayed here. So again, we might not necessarily know what angle B and E are. We may not necessarily know what angles A and D are, C or F. That's fine. But we know the relationship between them is that they are always going to add up to equal 180 degrees. So let's work with an example of we were told to solve for one of these angles. Separate these out here. So let's say we're told if angle, say D, is equal to, let's say, 110 degrees. Separate this out here a little bit better. So if we were told if angle D is equal to 110 degrees, I'm going to try and make this angle look a bit better, not like an L. There we go. If angle D is equal to 110 degrees, what is angle A? And again, in this instance, we know that angle A and angle D are supplementary. They add together to give me 180 degrees. So we can start with our general formula, our general equation. We know that these two add to give us 180. Then we fill in what we know. Ooh, don't know what that is. And now we just subtract 110 from both sides. And we find that angle A is equal to 70 degrees. So there's not a particularly whole lot of new math that we have showing up with this. I think the biggest part that is the challenge with a lot of 10.3 and I think even the 10.4 is making sure we know which property or which relationship we are using when we're working through these. And again, I think this entire chapter, all of chapter 10, lends itself very, very much to drawing a visual of what you are working with. A lot of people that struggle with this section and they come to me to my office hour say, I'm having trouble with this. Can you help me out with it? And one of the first things I'm always asking people, did you draw a picture? And as you guys can see with just on my drawings, I'm not an artist. I'm not expecting you guys to be an artist. But drawing something and making a visual of it goes a really long way, especially with geometry. So use that. It's very helpful with these. So this is one of our examples that we have of finding one of the missing angles. And again, doesn't matter if we've been given the exterior angle, doesn't matter if we've been given the interior angle. We're just finding that relationship between them, considering that they always add up to be 180 degrees. So again, just write it out for yourself, do some labeling, maybe set up some of these relationships for yourself up here as you need to, and then just fill in what we know and solve for what we don't know. So I'm going to jump us back to our notes. So we just worked with the triangle angle relationships. We're now working with classifying triangles by angle lengths. So when we have an acute triangle, that means that all three angles are acute. So We're back to 10.1. An acute angle is an angle that is less than 90 degrees. An obtuse triangle is a triangle where one of the angles is obtuse. We're back to our definition of that. An obtuse angle is one that is greater than 90 degrees, but less than 180 degrees. And then we have other ones, or other kind of unique one, which is a right triangle, which is where one of the angles measures exactly 90 degrees. And this, remember, has a little square that's going to show up in it. When we're going through these, and we'll go through a quick just kind of visual on what these might look like, they're probably going to end up giving you, here's a triangle, here are all or some of the important angle measures that you need, and then just choose which one that would be best to classify that triangle. So I'll jump us over to our whiteboard, just go through a couple quick visuals of this thing. Acute triangle. There we go. So acute triangles, again, all the sides are less than 90 degrees. So we have something like this. We have something like that. Doesn't entirely matter the angling that they're set up. But all of the angles inside are less than 90 degrees. I think a lot of triangles that we see more often than not are acute, but I can't say that with any exact certainty. I think the obtuse and the right triangles are significantly more distinct in this regard. So obtuse triangles, ones where we're going to have an angle that is greater than 90 degrees. And again, more often than not, especially with the obtuse triangles, we're probably going to be given something that says, hey, this angle right here, this is 130 degrees. Or something, another one up here. Oops, didn't show up too particularly well because it doesn't like to do that. Could say, oh, this thing is 160 degrees. And then if we're asked to classify this triangle, well, based on that property, this is obtuse. We'd select that. I think if I remember correctly, I think the homework problems have a drop down or a multiple choice or something to that effect. We'd choose obtuse, and then that's all that we have to do. So we're just classifying those things. Look at it, look at the properties and the information that we have regarding these, and then just select the right one. Not a whole lot of actual raw math involved in it. So then we'll go to our right triangles, which again, this is one that the right triangles have a really distinct, really obvious giveaway to them, which is nice. We have a triangle, and anytime you see that little square showing up in there, this square is the giveaway of that's a 90-degree angle. And right off the bat, you can just jump to that's a right triangle. We worked with these when we had the Pythagorean theorem stuff. Very important, very unique triangles. So again, that square showing up in there, that's the big one that you want to be looking for. There's a couple different ways that could be displayed. And again, with all of these triangles, it doesn't matter how it's oriented. It could be rotated slightly off center. It could be kind of reversed from maybe what we might think of drawing a triangle as. It doesn't matter. We are only looking at the angle and the angle measures. That's the giveaway for us. So if we see that, there's our giveaway, classify it, bam, done. Jump us back to our notes here. So that was working with our angle lengths. So now we're going to work with our side lengths. So other classifications for triangles. And this is going off of, again, two completely different things that we're measuring. One's with angles, one's with the actual side length themselves, if we were measuring these things. So an equilateral triangle is a triangle where all side lengths of the triangle are congruent, also known as equal to one another. The really nice part about equilateral triangles is if all of the side lengths are congruent, then all of the angles are also congruent, or they're also equal to one another. Equilateral triangles are really, really nice in that regard. The isosceles triangles, two side lengths of the triangle are congruent, or equal to one another. And similar to the equilateral triangles, they have this really nice property that if two of the side lengths are congruent, two of the angles are also going to be congruent, or equal to one another. So these two are our most unique types of triangles that we're going to be seeing through a lot of these in terms of our side lengths. Most triangles that we're going to see are going to be this third kind, which are scalene triangles. A scalene triangle is one in which none of the side lengths of the triangle are congruent to one another, which means every side length is different. This also means that none of the angles are going to be congruent or equal to one another. All of the angles are different. Most triangles that we're going to be working with in this class and most future classes, most triangles are scalene. If you were to just draw a triangle at random, you're probably going to have a scalene triangle showing up. So some of the ways that these can be displayed, we'll go through how these can show up in here and some of the visuals that show up from that. So we'll go over to our whiteboard. And I'm just going to move us back over here. Okay, so our first one that we had were equilateral triangles, some ways that we can see that show up. So equilateral triangles. So, and the nice part about this program is it does a lot of this stuff for me, but I'll show you guys the key points that you want to look for this. So an equilateral triangle is one where we've been told all side lengths of the triangle are congruent to one another. So the way that could happen, we've been given a triangle. Now I know this thing, the program auto-adjusted to make it look this way. Let's assume it doesn't do that. Let's assume that it's just a random generic triangle that's been given to us. There's a couple ways that they can display this triangle to tell us that it's equilateral. They can actually give us the side lengths of all three sides. So for instance, we could have a triangle with a side length of 3, 3, and 3. That tells me all the side lengths are the same. This thing is an equilateral triangle. Done. The other way this could be displayed, again, I'm looking for a right triangle here. There we go. Again, we've been given a generic triangle. I think this program automatically just makes equilateral triangles, but let's assume we didn't know if it was or wasn't. The other way that it can be displayed that all of these side lengths are the same is if we have a little line showing up. So every side that is marked with one line, it is implied and assumed that those sides are equal to one another. Now, we do not necessarily know in this instance what the actual side lengths are of this triangle, but those little dashes on the side lengths themselves tell us these three things are equal to one another. They are congruent. So while I don't know what they are, I know they're congruent. This is an equilateral triangle. I'm done. We can see very similar things show up with angles as well. I'm going to use the second one as an example. If we are told, okay, this angle, and this angle, the interior angles there, are the exact same. The angles could be displayed very similarly. They could say, that's not showing up as well there. Do this. There we go. So just like the side lengths that have those dashes in them, all of the angles that have those two dashes over them, we don't know their exact value, but it is implied by drawing it out this way that all angles that have that double dash in them are congruent to one another. So again, we know, are the angles all congruent? Yes, that's an equilateral triangle. Are the sides all congruent? Yes, we have an equilateral triangle. So we have two criteria that we can go with for classifying these things. Ooh. There we go. Okay. So work with the isosceles. Isosceles triangles are kind of cool. They're pretty unique with how they show up. So similar to our ones that we just went through, we were working with, we're going to go through a similar way of how we can display those. And again, very, very similar to the ones that we just did. Isosceles triangles have two side lengths of the triangle that are congruent. So again, that can be given to us by having numbers displayed. So this side length is 5, this side length is 5, and the bottom one, let's say it's 2. If two side lengths are congruent to one another, then I know I have an isosceles triangle. Done. Again, we could have it displayed just showing different ways this can show up. They could display this with the lines instead. So it could be those lines are there. And we have those ones there. So again, the dashes, the little lines that are showing up on each of these side lengths, tell us which sides are and are not congruent to one another. So that tells me, based on the dashes, this side length is congruent with this side length. Again, I do not know what that exact value is, but that's fine. This tells me they're equal to one another, so I have an isosceles triangle. We also have the instance where we might have the angles showing up. I'm using to go back to our first one here. So here's an angle there, here's an angle there. And again, I don't necessarily know what the measurements are for those two angles. I don't know the exact value of them, but that's fine. I've been told they are equal to one another, and that is all that I need to tell that this thing is an isosceles triangle. We can classify it, and then we're done. And then again, the last one with the scalene triangle, it's essentially, if we're given something, is it an equilateral triangle? No. Is it an isosceles triangle? No. It's probably a scalene one then. And again, scalene ones are, we have three completely different side lengths. We don't know what they are. Come on, thing, move. I'll move us over here a little bit. Go over here. So we could have scalene triangles show up again with numbers. We could have it be a, let's say this length is 5, this one's 7. I'm making up values here. I don't know if these would be accurate. It could be, I don't know, we'll say 10. So classify this triangle. Well, none of the side lengths are equal, which means that this thing has to be a scalene triangle. And that's all that we would do. If they were showing it with these lines, okay, we'll stick with this one. Or it wants to do that instead. There we go. We could have it written, instead of having actual raw numbers showing up in there, which happens from time to time, it could be written out with the lines of that, that, and that. Which again tells us none of these three sides are congruent to one another. So I have a scalene triangle, classify it, done. Nothing much we can do beyond that. Okay, so this is everything from the 10.3 material. A lot of what this is the homework might have for you, and if you are someone who is going to go and take a look at the book problems, a lot of those they're just going to be asking you to classify these things. They might give you different information. They might give you stuff on the sides. They might give you the angles. All you're going to have to do, go back into these notes and say, okay, what have I been given? Is it an acute triangle? Do I know something about the angles? Do I know something about the side lengths? And then just find what we have been given and match it with what we know in here. There's not a whole lot of actual raw calculations that go on with these. So we're going to move on into 10.4, which is the general idea of essentially shapes. Now 10.4, I think there's, and we're going to show it here, but there's a lot more information on here than what I'm going to be demanding or expecting you to know and have memorized for the test. Because there, as we can kind of see with the picture, and I'll go into this in here in a little bit, there's a lot that this breaks down to. There's a lot of vocabulary. There's a lot of different ways that we can and will be classifying and calculating things. I am not expecting you guys to have all of this memorized. If it comes time on the final exam when you guys are going through these, it'll probably give you the necessary information that you need. Here's a parallelogram. Here's some important information. I would also note to you guys that I mentioned the geometry info PDF. That's also available on our Canvas site. That's a really good reference for going through and using a lot of those formulas as necessary for the final exam, which you guys are welcome to use for that. But again, we're going to go into this and take a look at some of these breakdowns with polygons here. So our core definition of a polygon is a closed shape with sides made up of lines. So we have any number of polygons, squares, rectangles, octagons, hexagons, pentagons, triangles, all these different things. Can you make a shape out of lines? Yes. Congratulations, it is a polygon. I've got a whole bunch of them over here. I'm going to zoom us in a little bit because I'm hoping that that's showing up well enough, but just want to be sure. So within this overarching idea of polygons, we have quadrilaterals. A quadrilateral is a shape with 4 sides and 4 interior angles that adds up to being 360 degrees. Some special types of these quadrilaterals are trapezoids and parallelograms. So we have kind of our display over here. We have quadrilaterals. So we have these 3 main types. So irregular ones, where I've got 4 sides for both of these, but there's nothing particularly special about them. We could kind of make any 4-sided shape of them. We then have parallelograms, which have some unique properties to them, which we're going to go into here in a second. And then we have trapezoids, which they have kind of some unique properties to them, but they are less unique than these ones we have down here. So trapezoids primarily, it's a 4-sided shape that has 1 pair of parallel sides. So if we look at this trapezoid, we're seeing this top line and this bottom line are running parallel to one another. And that's the only requirement that we have for trapezoids is this line is parallel to this one. That's all we need. We don't care about if these are parallel on the sides. They could be equal to one another. They could be different. Who cares? So within our parallelogram is a 4-sided shape that has 2 pairs of parallel sides. So trapezoid only has 1 pair, parallelogram has 2. So some types of parallelograms that we have rectangles, we have squares, and we have the rhombus, or rhombi is the plural for that, where we can see these 2 sides are parallel, these 2 sides are parallel, these 2 sides are parallel, and then you look vertically, these 2 sides are parallel here, these 2 sides are parallel here, and while these aren't vertical, we can see that these 2 slope sides are parallel to one another as well. And again, these classifications and knowing all of these specific rules, it's nice to have them have a good idea of what those represent, but I am not going to be expecting or demanding that you guys can classify, okay, what specific type of polygon is this? It's this type, it's that type, it's that, and all the way down to the very specific name. It's good to have these ready to go. I think you want to know at least the rectangles, squares, and rhombus over anything else. These are the big ones because they show up very often. But beyond that, in terms of what I'm going to be expecting that you guys know, and I think your future classes in this regard, you're not going to need to memorize and know these inside and out. It's worth to having them having the reference of where to find this information is necessary, but it is not one where it's like, if you don't have this memorized, you're not going to pass the class. You'd be just fine without that. So continuing this on to our next page before we go into our example that we're going to go through with this. Our last definition that we have is for a rhombus, which is a more specific type of parallelogram, but it's 4 congruent sides, but does not have any right angles showing up in it. So we'll jump us back to our example. So 4 congruent sides, but they have no right angles. So again, our rhombi, it's our plural for rhombus. All of these sides are equal to one another, but we do not have any right angles showing up for these interior angles in here. And again, these are just properties of our polygons as we're going through and working with them. If you are working with the textbook, or if you would like to, I'd recommend looking at page 706 for a list of polygons and their properties. There's a whole big list of those in there. Again, you are not required to know every single property for every single polygon, because that is just, to me, that's not really something that's worth testing you guys on when, if we're honest, why not just Google it? So it's worth having, I think, triangles, squares, rectangles. I would have those ones nailed down. Maybe even a rhombus nailed down if you're thinking on that one. But yeah, a lot of the other ones and their properties, I don't see it as worth your guys' time to test you on. Can you memorize these facts in that regard? I don't think that's particularly useful. So we're going to go into our example that we have here. We're going to be classifying all shapes and missing angles of the given diagram. And this is something that I could display and give to you guys on the final exam. So basically what we'd be doing, I would probably adjust these numbers or maybe the shapes a little bit to make it so we have our, it's not as intense in terms of what I'm demanding that you guys have known with those. So classifying all shapes and missing angles in the given diagram. So let's work with some of these shapes. So we can only build so many shapes based on how many points that we have to work with. So for instance, we have the shape that's created from the points B, M, C. So I'm going to move us, adjust the screen here a little bit so I can have the display and draw off to the side. So I have a shape that's made out of points B, M, C. This would be classified as a triangle. So the way we do that, we display that for ourselves, we would write out triangle BMC, triangle. So I'm just looking at the shapes that I've been given, and what does this display as? It may also show up for you on the homework or otherwise without having this little triangle part in front, and it will just give you these 3 letters. And when they give us just letters listed like this, that means if you were to go from point B to point M to point C and then connect C to B, what shape is displayed when we do that? So B, M, C, those are my 3 points. What happens or what shape is created from that? So that's the kind of questions that we could be seeing that as well. So let's take a look at the point or the shape made from, oops, I'm sure I'm looking at the right stuff here. A, M, D, E. That's points A, M, D, and E. And they all connect together. So if we're looking at this, okay, it's got 4 sides to it. But based on our classifications and our information that we just went through, it's not a square, it's not a rectangle. Looking at this, I'm saying, well, I've got some of these things that, yeah, they look like maybe this vertical line here is parallel. Maybe this vertical line here is parallel. I have not been told that explicitly in this problem, so I cannot make the assumption that this thing, that this line and this line are parallel. If I was told that, then I would have a trapezoid, because our definition of a trapezoid is a 4-sided shape with 2 lines that are parallel to one another. But because I have not been told that information explicitly, all I have is a 4-sided shape with some properties that are going on inside of it. So because of that, I really can't get to any specific 4-sided shapes on here. So I do have to leave this as the generic, what is this thing? It is a polygon. I can't really classify it as anything beyond that because I have not been explicitly given any other information in that regard. And our last shape that we're going to look at is the shape A, B, C, D, E. So again, we're looking at points A, B, C, D, E. Now this is one where if we have this list of polygons up for ourselves, I don't think this one was listed on our exact, the list of notes that I have here. We're saying, what can we classify this shape as? Okay, it's got 5 sides to it. And if we were to take a look at that list that we have on there, we would find that this thing meets the bare minimum qualifications for being classified as a pentagon. I think there might be a couple subtypes of pentagons in there, but I don't believe we have any other additional information that we need to make to classify it beyond that point. So what shape is created from points A, B, C, D, E? It's just going to be a pentagon. And that's all that we would do there. So those would be the 3 shapes that I could ask you about. Those are the 3 types of answers that we could have. We'd be good there. And again, if you're going through these and you're thinking to yourself, well, okay, but the second one that we did, it kind of looks like it could be a trapezoid. Maybe you could look at some of these other angles and say that something could be parallel. You could make an argument for this. You can make an argument for that. And I will agree with you that there are arguments that could be made for it. To me, the fact that the conversation would have to come up of, and we have to argue about what this shape is or contest this point of an argument, that to me is not worth your guys' time on testing you on that. If I'm going to give you a shape or give you something that you're going to work with, it's going to be pretty obvious what it's going to be. Or I'm going to give you all the information to make it as abundantly clear as possible. Here's what it is. And again, I think a lot of these classifications are not necessarily the most worthwhile thing to grade you guys on as well, or test you guys on as well. There are more pressing things to test on. But let's look at 3 angles that we can work with here. So let's say we are asked to calculate angle BMC. So angle BMC, the one that is created from points BMC. So I need to find this angle right up here. Now, based on what we just went through, one of the properties of a triangle is that all of the interior angles add up to equal 180 degrees. So I know angle 60 plus angle 60 plus this remaining angle adds up to be 180 degrees. So you could write that out for yourself. We'll go right below here. Actually, I'll scroll us down here a little bit. I know that, oops, give me the draw. 60 plus 60 plus angle B M's. Oh my goodness. It's not cooperating with me at all. Angle B. Come on. Okay. I'm not sure if all this is, if you guys are still able to hear me or not. My screen has frozen on my end, unfortunately. So I'm going to end up having to restart my computer here, and I'll be right back into the lecture once this is up, and we'll finish up the last of this from here. Essentially, the last of this, we are just going to be using our properties that we know about interior angles, adjacent angles, and things like that. So I'm going to blip out here, and I will return, and we'll go through the last of these, hopefully in just a couple minutes once this restarts. Okay. Hopefully we're back and good now. Okay, so we were at, jump us over to,